Good morning. Today we are going to discuss about the conduction in extension to the previous video. So, let us discuss once again what is conduction. Conduction means heat transfer through the one molecule to the another molecule in the medium or throughout the medium by means of vibration. See here, there is no mixing of the molecules which causes a heat transfer. Okay, the heat transfer is going to happen by means of vibration. So one molecule absorbs the heat energy and that vibrates the same. Because of this vibration, the heat is going to transfer from this molecule to the another molecule. In such a way, from molecule to the molecule, the heat is going to transfer, and throughout the medium, the heat is going to transfer. So let us discuss about the conduction. Here conduction can be explained by means of three equations, under which first one is Fourier's law, and second one is steady state heat transfer, and third one is unsteady state heat transfer. So by using these three equations, we are going to study the heat transfer by means of conduction. So let us see with the first equation, that is Fourier's law. See, Fourier's law says as the heat transfer is going to happen with the temperature difference between two areas. So this leads to the flow of heat. So let us see it by means of equations. See, the heat transfer, that means dq by dt, rate of heat transfer, is directly proportional to the temperature difference between two molecules or two areas. As well, it is indirectly proportional to the resistance which is offered by means of the medium. So in such a way, we can derive the equation where rate of heat transfer is equal to the temperature difference between two molecules or two areas divided by resistance offered by means of the medium. In such a way, we can discuss about the Fourier's law. See, the complete equation for Fourier's law is dq by dt is equal to minus k into a dt by dx, where the rate of heat transfer is directly proportional to the difference, temperature difference between two areas through a unit flow path. dq by dx means unit flow path. So dq by dt is directly proportional to the dt by dx, where dq by dt is equal to minus ka dt by dx, where k is called as thermal conductivity. Thermal conductivity is known as rate of heat transfer by means of conduction is going to depending upon the unit cross-sectional area having temperature difference through perpendicularly, so which is called as thermal conductivity. By using this thermal conductivity, we can know about the heat transfer or heat transfer by means of various kinds of material. So if you see here, see kind of material at a particular temperature and what it is having the thermal conductivity. See, for example, if you take the examples for solids, for metals, silver and copper are the examples, and for non-metals, glass and carbon are the examples. Carbon means graphite is the examples, where silver at 100 degrees centigrade it is having thermal conductivity of 238, as well as for copper it is having at 100 degrees centigrade it is 218. As we know that silver is having more heat transfer when compared with the copper. So this one we are going to study theoretically by means of thermal conductivity. This is having more thermal conductivity, that's why it is having more capability of heat transfer. In such a way, we can discuss about the same. As well as if we consider the non-metals, see at 50 degrees centigrade, glass is having thermal conductivity of 0.69, but carbon, graphite is having 80 at the same temperature. That means carbon is having more rate of heat transfer compared with the glass. So this one we are going to study by means of the same. So coming to the next one, liquids, mercury at 0 degree centigrade it is having 4.8 thermal conductivity. Water is having 100 at 100 degrees centigrade 0.39, as well as for gases if we consider, air is having 0.018 at 100 degrees centigrade, and steam is having 0.0136 at 100 degrees centigrade. In such a way they are having the thermal conductivity. Usually thermal conductivity is independent of temperature difference. See, where thermal conductivity is equal to A plus B into T, where A and B are the constants, and what are the units for thermal conductivity? Joule per meter second degree centigrade, or watt per meter as well as hour. Okay, in such a way we can know about the units of thermal conductivity, where A is nothing but the heat transfer to a particular unit cross sectional area, as well as already we have discussed dt by dx is nothing but a particular temperature difference through unit path. Dx means unit path, so which is called as this one. So in such a way, by using Fourier law, we can study about the rate of heat transfer. So rate of heat transfer is directly proportional to the temperature difference. Coming to the next equation, that is a steady state heat transfer. When heat transfer is termed as a steady state heat transfer, when heat transfer is not affected by means of the time, that means dq by dt is not affected by time, then such a heat transfer process is called as steady state heat transfer process. Let us discuss about the equation. Okay, where dq by dt is termed as q by theta or small q. So when we are going to write in Fourier's law equation q by theta as well as small q instead of dq by dt, it means heat transfer follows steady state heat transfer. That's why for a particular heat transfer process by means of any mechanism, we are going to depict by means of different kind of letters. Okay, so in this we are going to write the equation based upon q. So the Fourier's law of equation turns into the q is equal to minus ka dt by dx. See, usually what do you mean by negative sign? Negative sign means transmission of heat from hot heat to the cold heat condition. Okay, so that means here loss of heat is going to happen from hot heat to the cold heat. That's why we are going to depict it by means of negative sign. So as well as we know that K means thermal conductivity, A means surface area through which heat transfer is going to occur. Okay, where dt by dx is nothing but temperature difference with respect to the unit flow path. In such a way we can discuss about this equation. So finally this is the equation using which we are going to write the rate of heat transfer through the steady state heat transfer process. Okay, so here let us discuss about heat transfer through a slab. That means if a slab is having two faces in it, okay, and it is having a particular surface area A, it is having a particular surface area A, as well as one surface is having T1 temperature and another one surface is having T2 temperature, okay, as well as having a thickness of X. Okay, in such a way, if it is having some parameters, then how we can write the equation for heat transfer within the slab? So if we consider T1 is greater than T2, then we can write the equation for heat transfer where Q is equal to Ka T1 minus T2 by X. Okay, where we know that this T1 minus T2 is equal to the delta T. That's why we are going to substitute in this one, as well as we know that T1 is greater than T2. That's why we are going to write it as T1 minus T2, that equal to the delta T, as well as X. X means thickness. Okay, that means through a cross sectional area of the slab, the heat is going to transfer. That one we are going to depict by means of the X. So this simulates dt by dq. This simulates dt by dx. It is simulating the dt by dx. So the same we are going to write the equation in such a way. So this is the equation, q is equal to minus k into a into delta t by x. Okay, in such a way we are going to use to write heat transfer through a particular slab having two phases, as well as if it is having three layers in it. If it is having three layers in it in such a way. Okay, so this is T1 and this is T2, this is T3, this is T4, as well as first layer's thickness is x1 and second layer's thickness is x2 and third layer's thickness is x3. In such a way we can write the thicknesses also. So how we can write the equation for rate of heat transfer when a slab is having three layers in it? See, this is the equation. If it is having three layers in it, we can write the equation in such a way where rate of heat transfer is equal to K1 A1 delta T1 divided by X1, that is equal to K2 A2 delta T2 by X2, that is equal to K3 A3 delta T3 by X3. That means heat transfer is unique in each and every layer. That's why we are going to write down the equation in such a way. So if you simplify that equation, the equation turns to Q is equal to UA delta T, where U is nothing but overall thermal conductivity. That means U is equal to, okay, K1 plus K2 plus K3, okay, as well as where A is nothing but A1 plus A2 plus A3. In such a way, we can write about the delta T equation also, where delta T is equal to, okay, where delta T is equal to T1 minus T2 plus T2 minus T3 plus T3 minus T4. In such a way what we can do, we can write the equation for the same. So in such a way, okay, we can write the equation for the overall heat transfer. That means Q is equal to UA delta T, where U is called as overall thermal conductivity. In such a way we are going to write the equation. A means overall surface area, overall temperature difference, delta T means. In such a way we can write the equation for the same. So this is about the steady state heat transfer. Coming to the unsteady state heat transfer. Unsteady state heat transfer. See, unsteady state heat transfer is known as where rate of heat transfer is affected by means of the time. When it is not affected by means of the time, then such a heat transfer is called as steady state heat transfer. When it is affected by means of the time, then it is called as unsteady state heat transfer. See, for this we cannot explain the Fourier's law equation because it is having complexity. That's why we are unable to explain the, or it is difficult to study the equation which is used to study the rate of heat transfer through the unsteady state heat transfer process. See, generally cooling as well as heating as well as sterilizing of the pharmaceuticals comes under the unsteady state heat transfer. So all these are about the conduction process.